Hello. In this video, we'll pick up where we left off in Monday's class. So we had initially started talking about frequency tables. So right now, I wanted to jump right back to where we were. So in this little table, I've got a frequency table, I've got categories, and I've got the frequency. Specifically, we surveyed children to determine their favorite color, and the results are given below. Now, we did actually start the other day by making a frequency table by literally taking the results blue, blue, green, red, blue, green, purple, red, blue, blue, orange, and then putting it into that table. So there are some homework problems and you should be able to do that. But for this, I wanted to pick up with the relative frequency. So right now there's no problem yet. So again, we should be able to make this if I gave you a bunch of data, just blue, green, red, purple, to sort and organize. All the favorite colors are listed here. You can't skip categories. Here are the frequencies. Little things, here I put them in an order from most frequent to least frequent, but as long as technically everything is here. So, if I asked you to make the frequency table and someone else had green with 26 and then red with 21 and then blue with 57, as long as you have all the right colors and the right frequencies, it is correct. Again, there are some preferences. People like to try and put some things in order, so most frequent to least or vice versa, but it's not essential. So this part is done. What I want us to start with is, now that we have that, I want us to determine the relative frequency. Determine the relative frequency. So we're going to add one more column, and this one will be for the relative frequency. The way to find relative frequency is literally the fraction of values that appear in each category. So that formula we had the other day, the frequency from one category over the total number of sampled items. So here, I told you we survey children, and sometimes they tell us how many children or how many objects. Sometimes that information is given right off the bat, but not always. And here it was not given, so for us to determine the relative frequency, we have to figure out that total. So that's where, I'm jumping ahead a little bit, but we often use the lowercase letter n to stand for number, right? Just to have that connection, the number of values, the number of objects. So here, the number of people who were surveyed. And we could figure that out by just simply adding this column. So I'm just going to go through and do that quickly. We got 57 plus 26 plus 21 plus 17 plus 9. So it appears we had 130 children who participated in this survey. So for the relative frequency, we're literally just getting the fractions. So the relative frequency for people for children who favored blue would be 57 out of 130. For green would be 26 out of 130. Then purple would be 21 out of 130. Red was 21 out of 130. Purple is 17 out of 130. And then orange is 9 out of 130. So that is correct. But we mentioned in class the idea of fractions, decimals, and percentages, and right now I want to pick up on that. So if you are actually doing this, in a few moments we'll take this information and then we'll make a pie chart. And the pie chart, I know I haven't introduced that yet, but the pie chart is that each category occupies a piece of pie that's supposed to be the same as its relative frequency, so that we could visually see the chunk of pie that would go with each of the particular categories. So if we just leave these as fractions, that's very hard to determine. So the easier way would make it a decimal so we could see that as a percentage. But in this one, the one we did in class the other day, we had 25 people. I think it was the student grades, and we had 25 students. So you notice when we looked at the decimals, dividing by 25 works out pretty nicely. So you get pretty nice decimals. But this time, look at what happens. 57 divided by 130, and look at that ugly mess. So just to realize, we need to round. right? We're not going to copy that. That's not an exact number because this decimal keeps going even though the calculator stops. So we've got to round off. So good habits. For something like this, 3 decimal places is a pretty good way to go. I know some people try and cut it down to 2, but it's a little bit better to be, almost extra efficient. That extra decimal isn't going to hurt anything. Not here. There are a few specific contexts in statistics where you don't want to use too many extra decimal places, but that's not this situation. So right now, if I want to round to the 3rd decimal spot, then I look at the 4th. And if this digit, 5 or bigger, I round this number up, 4 or smaller, you round down. But I always hate that expression because if this was a 5, we'd round this up to a 9, and everybody understands that. But when I say round down, now all of a sudden some people make that a 7. No. When you round down, you just go back to this decimal. So this would be approximately 0.438. And that's 43.8%. For those who are, again, just trying to make sure you're good with the conversion back and forth. So let me keep going. 26 divided by 130. This one does work out clean, right? It's not always. This isn't, I don't want to get into what denominators are good versus what are bad, but just to realize this looked ugly, but now this one is nice. We get a nice clean 0.2, and that would be 20%, not 2%. You still have to move the decimal 2 places. So if you want to put that extra 0 here so that you can clearly see it's 20% here. Then 21 divided by 130, another ugly decimal. Now again, here, how far do I round? Well, there's no decision, right? It was a nice, easy decimal, so nothing to worry about. But now we got another ugly decimal. So let's be consistent. We rounded this to the 3rd place. We'll do the same thing here. So I look at the 4th spot. One big thing, actually, let me go back to that first one for one moment to point out, don't double round. This is a perfect example. People see this is a 6, so they want to round this up to a 5, and now this is a 5, so they want to round this up to a 9. No, that's double rounding. That's rounding twice. We only do it one time, so it's just this decimal tells me what to do here. This is a 5. I'll round this up. I get 0.162, which is 16.2%. 17 divided by 130. Again, same thing. I don't care about this. I look at this one. That's a 7, bigger than a 5, so I round that up. I get 0.131, or 13.1%. Oops, I should be writing approximates here. This one was an actual equals, but these, again, were rounding. It's not the worst thing, but it's just good habits just to get used to. And then last, 9 divided by 130, 0.0692. Just quickly to realize, if this was a 5, we'd round this one up, which would make that a 70, right? That would become a 10, which we'd have to bump that over. But we don't have to worry about that here. That's a 2, so we round down, 0.069. 6.9%. The second quick thing that we pointed out in class when we had the relative frequency, everything has to be represented here. There's no skipping categories. There's no skipping individual data values. You can't skip people's answers. So at the end, if every person is represented here, this has to add to 100%. But to just realize that now we did some rounding. Again, you go back and look at the one we did with the letter grades in class. That adds to a perfect 100%. Here, just to note, let's see what happens. Plus 20, plus 16.2, plus 13.1, plus 6.9. And it does round off to a perfect 100%. The reason that happened to work out was that we had 4 rounded answers, and it just kind of coincidentally worked out that 2 of them rounded down and 2 of them rounded up. But there would be situations where it's just not perfect, that maybe 3 of them rounded down and 1 of them rounded up, and we'd get something like 99.9. Or, maybe 3 of them rounded up and 1 of them rounded down, and we get something like 100.2. That shouldn't bother you, everybody. That we should just look at and say, oh, that's a rounding thing. This is on the right track. But if you added this up and you got like 93%, no, something's wrong. Either you made a mistake with your computation, you made a mistake while actually doing the decimal work, miscopying, but that should be a big red flag that something went wrong. Okay, so frequency tables, very, very commonly used. One of the first things we do, we have a bunch of data. What do we do with it? Well, trying to organize it in some sort of a table. So all categories are clear, and we clearly see how many people, how many objects fall into each category. And this is nice, but again, this gives us a better sense. If I told you 77 college freshmen say that they smoke more than 5 cigarettes a day, well, is that a lot? Is that a little? I'm not counting the number of cigarettes, but the number of students. Just saying 77, well, it sounds like a lot of students, but did we survey 2,000 students? Did we survey 200 students? That makes a big difference. So the frequency total, when looking at all of them together, can help us sort and get a sense of, what people's preferences and favorites and things like that are, but the percentages really help us a lot. So it's not just a raw number that we could see, okay, look at that. That's not half, but it's getting fairly close to half of the children liked blue. And then we got a nice, smattering of here and there of other colors that the kids liked. So just trying to point that out. The next thing that we also talked about in class was the difference between qualitative data versus quantitative. The easier way to distinguish the difference between these two is to get a little extra word here. Qualitative is categorical, and quantitative is numerical. So again, we did say this in class. So very quickly, that first example, we looked at what letter grade did you get on the test. So you got an A, a B, a C, a D. That is categorical data. Basically, when we say categorical, this is not perfect. I'll explain the tiny little trouble with this. But for a lot of people, it helps to just think of it as non-numerical. If I asked you what number grade did you get on the test, instead of, you giving me I got an A or I got a B, you're telling me now I got a 94, I got an 86. Well, now you're giving me numerical data, and now that is quantitative data. Now, there's one tiny little catch to this. I don't want to harp on this too long, but just to realize, the reason that's not exactly perfect is that technically there's this extra part to quantitative. In the book, they formally define it that it represents counts or measures, okay? So when you say that, representing counts or measures, that's already implying something a little extra. That it's not just having a number, that number actually means something. So for instance, if I asked you, what is your first name? Well, that's clearly categorical data, right? But if I asked you, what is your ID number? That feels like it would be numerical data, but that number doesn't mean anything. Your number is 123, my number is 125, his number is 478. Those numbers don't tell us anything. It's not like saying I'm 64 inches tall or I weigh 175 pounds, where now we could literally use that to compare to someone else to say that person is taller or that person weighs more. But the ID number is just literally a way to identify someone, so that technically falls in categorical. But I don't want to confuse you with that. I wanted to point out that there is that subtle distinction. But now let's just go through a bunch of examples. Is the data qualitative or quantitative? And, something like favorite color, that is qualitative data, right? We're getting answers like blue, green, red, purple, orange. We're not getting number answers. This is a very easy way to get confused, everybody. People see numbers over here, that at the end, we do count how many people preferred blue or preferred green, but the actual data you're collecting, you didn't collect this, you collected the favorite color. So similarly, let me ask a few questions here. Is the data quantitative or qualitative? I ask you, how long does it take to get to school? Now, just to be clear, we made a very big deal in the last class talking about population and sample, identifying who is the everybody versus who you are actually surveying, collecting information from. But for now, I'm just kind of jumping to the question that gets to the variable, that gets to what we care about, what we're actually measuring, collecting, what information we're gathering. So here, who are we doing this for? Am I doing this for a bunch of elementary school students? Am I doing this for Queensborough Community College students? We could, that information needs to be clear to discuss population sample. But for right now, I'm focusing on the data. So just thinking about that. How long does it take to get to school? It takes me 25 minutes. It takes her 37 minutes. It takes him an hour and a half. Now, when we collect that data, we try and have the same units. So if a lot of people, their answers are coming in minutes, maybe we convert that person. Instead of saying it takes 1.5 hours, we'd say that takes 90 minutes. But realize the point is all the data we're collecting is numerical, that this would be quantitative. Okay, let's keep going. Number 2, let's still focus on school. What method of transportation do you use to get to school? Again, same thing. I'm just jumping to the question itself that's trying to talk about the data that we're receiving. I'm not clearly identifying a population or a sample here. Again, am I asking the kids who go to the high school across the street? Am I going to Queensborough? Am I talking about CUNY? Am I talking about universities? We've got a lot of different possibilities that would shape the population and then the sample we'd be looking for. But for right now, the method of transportation, well, I drive to school, or I take the bus, I ride my bicycle, I walk to school. All those are good possible answers, and all of those are categorical answers. They are not numerical, they are categorical. So very different types of categories than favorite color, but still categorical. This one would now be qualitative. I really like these extra words here. There are some books that use them as synonyms. Qualitative data or categorical data, quantitative data or numerical data. Our book only uses these two terms. So again, I like these terms to help, but to be clear, you got to be able to link these together. So these words are very similar, so it's very easy to get confused. You kind of have the idea of what you're looking for to answer the question, but to forget which one is qualitative versus which one is quantitative. Just for some people, the idea of quantity, a quantity is a number, right? What is the quantity of apples that you have? What is the quantity? Any of those things have some sort of that numerical measurement. So for some people, that tries to help them connect these two words together. There's no good way to do that here. People see the word quality in the word qualitative. Well, there's no, it's a good product or it's a bad product. That's not what's being discussed here. The type of data, it's not about good or bad data. It's all about numerical or non-numerical. So, qualitative or quantitative, we'll do a few more of these next week in class, but that's really the idea, just that simple. What are you asking? What's your preferred shoe brand? What kind of car do you drive? More categorical type questions. How much did you spend on food last week? How much money do you earn? How tall are you? Any of those types of questions. We're getting numerical answers back over to quantitative. All right, so now as we're moving along, introduce the idea of a frequency table. The book does a quick little discussion about binning data. A frequency table, when you have categories, is perfect, just like this type of situation. But let's just think about test scores for another minute. When we were doing test scores and we were talking about letter grade, well, it was very easy to set up your category, and the categories were letter grades, and we had A, B, C, D. But now we look at test scores. Let's assume our test is out of 100, and then, we're already getting ready for a frequency table. So test scores versus frequency. But test scores, if my test is out of 100, and if I want to list all my categories, I would literally have to list every single test score. 100, 99, 98, 97, 96, 95, 94, 93, 92, 91. And that would be ridiculous. The point of having this type of a setup of frequency table, or later on bar graphs, sorry, I'm just straightening my line, it was a little crooked. The point of making these things is for that organization summary. It's supposed to be helpful. Instead of, like we said in that first day, instead of just looking at all the letter grades just laid out, to be able to quickly see in a chart and see, this class did well, this class did okay. There are lots of A's, there are lots of F's. Very easy and quick to see those things. So now all of a sudden, if I start making a frequency table that has 100 categories, I've completely lost that efficiency and that effectiveness. So point is, if you have numeric, quantitative data, we can still make frequency tables, but what we commonly do is we group numerical values together. So this is on page 313 in your book. And this is a part of the packet that I attached. You've got some of these pages. And notice, how did they group those test grades together? Well, sometimes you would be told specifically, but sometimes it's up to you. They group them in bins of 5. So everyone who had a 95 to a 99, everyone who had a 90 to a 94, an 85 to an 89, and so on. We easily could have said, instead of doing this in groups of 5, and basically splitting the 90s into 2 groups, the 80s into 2 groups, the 70s into 2 groups, and so on, we could have grouped them in groups of 10. I could have went from 90 to 99, and I would have had 3 people in that one category. I could have grouped 80 to 89, and then I would have had 6 combined people in that one category. And similar down here for the 70s. So that's all they mean by binning data, and I think there's 1 or 2 problems in the homework, but they tell you how to set up that bin. But it's still the same idea, that you'd still have your categories here, you'd still have your frequency, and then you could also do a relative frequency. I mean, the book talks about cumulative frequency as well. Don't worry about that. But relative frequency is definitely something you should be able to do. So now we move into bar graphs and pie charts. What I want to say here very quickly is just every single type of chart we make, we need to be very clear that everything needs to be well labeled. That whenever you make a graph or a chart, sometimes it's about, this is just a table, but that table should not just exist by itself. We need to be very clear. What are we looking at? Well, it's favorite color. Okay, frequency. But where did this come from? Well, we surveyed children. We could even do a little more, be specific. What children? Where do we find these children? I surveyed children at the local county fair to determine their favorite color. But it shouldn't be vague. It should be clear every time you're looking at a table where that data came from, how it is being organized, so that people can see and get the right information out of it. So, specifically, a title or a caption, that your vertical side should be, numbered, that your horizontal scale, the left-right line, should also be clearly identified. If there are units being used, right? When I was asking you about how long does it take you to get to school, well, maybe we decide that units should be in minutes. So everything is in minutes. Well, that should be clearly identified. So that's where, those are the little things that are very easy to miss. A legend, if there are multiple data sets on a single graph, it should be clear. Like maybe we're using different color bars. These will be things we get to a little later on, like maybe just next week, not way later in the semester, but just next 2 sections, this comes up a little bit more. I would also include here any scale. If you use a scale, it should be a reasonable scale. I'll talk a little bit more about that. But if you like looking at these frequencies, if we were going to look at a bar graph where the highest frequency is 7, we shouldn't be labeling 10, 20, 30, 40. It's like, no, make the scale useful so that people can see clearly. If these were like 100 people and 27 people and 38 and 38 and 75 and 42, now maybe I would go up by tens. So your scale should be appropriate. They give you a little formula for pie charts, but I'll get to that in a moment. But right now, so I'm kind of jumping ahead a little. The first thing I should say is that once we have a frequency table set up, the fact if our data is numerical or if it is categorical, that kind of leads to our next display. And that if we have categorical, qualitative data sets, that's where we prefer bar graphs and pie charts. At the end of this, we'll finish with what if we have numerical, and we'll see we have two other displays that we like for numerical data sets. So this is what we're looking at. Now, let's jump right in. Again, there are some nice ones in the book if you want to flip through, but what I would like us to do right now, here we go. So we've got page 314, and if you're looking at page 314, they go back, they took the grades that we did in that first problem, the letter grades, and they made it into a bar graph. And what we see, the letter grades go across the bottom, it's identified as grade, all the letter grades are clearly identified. The frequency goes on the y-axis, technically, right? We very rarely put the relative frequency here. That really, I gotta be honest, that shouldn't be here right now. For a regular bar graph, we base it off frequency and category. And then you make bars for each category, and they note little things. The bars do not touch. We have very clear, distinct bars. This bar represents the A. The top of the bar lines up with the frequency. 4 people got an A. 7 people got a B. 9 people got a C. 3 people got a D. And 2 people got an F. That is a nice bar graph that goes with, again, that very, very first problem that we were looking at, that we did in class on Monday. But now, I'd like us to make a bar graph for this data set. So let's make a bar graph for favorite color. So, I should have also pointed out the last thing, right? There was a title here. You know, sometimes it's not just a title, sometimes a quick explanation, but all those components. Somebody looks at this, they weren't with us in class on Monday, but they could still look. Okay, what are we looking at? We're looking at the grades on an essay. They collected data, and that's the actual data. We could see the actual grades, we could see how many, and all that information that we had on that table is now clearly presented in this bar graph. And little things, why would we care about a bar graph? Well, one of the reasons we care is because it's a visual clue. You know, when we were talking about just looking and having it organized so I could see how many people had A's, how many people had C's, this adds to that. Then now looking at the peaks, well, it draws our eye to realize C is clearly the biggest category, that we drop a little bit on both sides. There are fewer people who had A's and B's, fewer people had D's and C's, more people on the upper side of the scale versus people on the lower scale. So it's just a lot of quick visual clues. Is this better than the frequency table? No, not at all. It's just an alternative. A lot of people like to present both, and sometimes you only get one or the other. So let's come back, and like I said, let's make the bar graph. Let's make the bar graph for our children's situation. So I'm going to set up my bar graph. Notice, everybody, I'm doing this by hand. You don't need a ruler or a straight edge. We do our best. If our lines are really crooked, like I saw here, try to straighten it out. If it really ends up ugly, just do it again. So we're going to get favorite color across the bottom. here's my title. We're looking at favorite color of children, and that's across the top. So here are the favorite colors. The favorite colors we saw, we had blue, we had green, we had red, we had purple, and we had orange. Just extend my line a little bit more. Those are all my favorite colors. But now, before I start making bars, I got to look at the frequencies, and I got to think about a little bit of scale here. Because again, that first problem that we just looked at a moment ago, the highest frequency total was 9, and everything nice single digits, so it made a lot of sense to literally go 1, 2, 3, 4, 5, 6, etc., going up the side, literally making each dash represent one single unit. But if we tried to do that same thing here for favorite color, well, now you've got to do 57 dashes to get to the top. That's kind of ridiculous. So just looking at the values themselves, thinking what's reasonable, well, now with this kind of data, we're in the 50s, the 20s, the teens, maybe grouping, kind of again that same thing with the bin idea, maybe doing a scale every 5 or every 10. Sometimes we would be specifically told what to do, but if it's up to us, just to try and be reasonable. If I go by every 10, I don't have to go past 60, because, why bother having 70, 80 going off the top of the chart when this is as far as we go? So I'm going to do that. I'm going to go by every 10. So this is my frequency. And some people explain that with a little more detail. That frequency here literally stands for, again, the number of children. It gets a little repetitive here. Favorite color for children, that we keep kind of repeating that. But frequency works. Like I said, I'm going to go by 10. Like 10, 20, 30, 40, 50, and 60. So now looking at my values, blue is at 57. Now, of course, here's the limitation. When you have literally every single number value marked off, you could see exactly where that bar lined up. So again, back in the letter grades, no ambiguity at all. This bar clearly lined up with 9. This bar clearly lined up with 7. But now, 57 is about somewhere up here. So I've got to make my bar go up there. And this is why, why would we include both a frequency table and a bar graph? This is one of those reasons. I could look at this, and now again, this shouldn't really be there. The bar is here and here, my scale markers. So if someone lined this up on the side, hopefully they'd be looking and say, well, what is that? Well, it's a little less than 60. It's more than 55. Maybe they think it's 56. Maybe they think it's 58. So sometimes people include the actual number on top to make that clear. But even if you don't include that number, it still gives a good representation, right? Next is 26 for green. So I got to get just a tiny bit more than halfway up between the two. So green is lining up about here. Red is only 21. That's going to be even lower, so about here. Purple is at 17, so now I'm looking at something about here. And lastly, orange is 9. Trying to make sure that's lining up just under the 10 marker. And like I said, not a bad habit when you can't exactly see where they line up to include that second value here. But again, the quick things. We're mostly concentrating on just making the graphs today, but just thinking that little bit further ahead. And again, now we can clearly see things. Look at how much higher this bar is compared to the others. Blue was the overwhelming favorite when it came to favorite color, right? More than double here, more than double. Our eyes like that extra sense of scale and proportion. So there are our bar graphs. Now the next thing, we talk about the pie charts. Now we need the relative frequency. Now, unfortunately, when I printed this out, it comes out black and white, so it's not as easy to see. But you will, if you actually look at it, you'll be able to see that here's your A piece of pie, your B, your C, your D, and your F. Now, like I mentioned, the book has this whole procedure about how you use the relative frequency times 360 degrees to figure out the angle that each piece of pie should go with. I mean, to be perfectly literal, that is one way to do it. But if you really want to do that, well, now you might as well have a protractor to actually get those angles correct. But just like we were seeing with the bar graphs, I don't need a ruler and a straight edge to do something like this. And I'm not going to need one for our pie charts either. What I'm going to show you, again, our pie charts, just like these bar graphs, it's a nice rough approximate that our eyes can visually see. So if you're looking at a pie chart, well, I draw my pie, so basically just a circle, and this is the better way. And this is why I was talking about having your relative frequencies as percentages. Because we can look, again, it's not a perfect circle, so let's do our best to try and get the middle. And from the middle, 1/4 of the circle represents 25%. So if you have a relative frequency that's in the ballpark of 25%, well, if it's a little more than 25%, you try and get just a little bit of a bigger piece of pie here, okay? I mean, some people, remember, I don't want to go crazy with geometry, but for the 25%, you literally have a right angle inside of here, and you'd be looking at 1/4 of the entire piece of pie. If you have values that are a little less than 25%, well, now you'd be looking for a little less than that quarter. Maybe something like this is about 22%, something like this, 20%. So just to use that as a ballpark, directly across, now all of this would be 50%. So just to use those as rough ballparks. So now we made a bar graph for the favorite color of children. Let's now make a pie chart. First things first, this comes up, you are given a frequency table right off the beginning here. Now, my first exercise, I had us make the relative frequency, but if this was never here, you could still go right to the bar graph, no difficulty with that, but for the pie chart, this would have to be done. So my simple point is, even if I didn't tell you to find the relative frequency, step one in making a pie chart would be to find the relative frequency. And now I'm going to do all that same stuff we were just talking about. So this was rough, and at the end, if we're looking at a couple of pieces of pie that are close, and we'll see that in our example in just a few minutes, a couple of pieces of pie that are relatively close percentages, well, then they should look like relatively close, the same size pieces of pie. But if one is bigger than the other, we should see that. So for us, look at these percentages. Not great. Nothing so close to 50 or 25, but a decent ballpark. This, it's not very close to 50, but it's kind of close. So don't give the whole half. Knock a little chunk off. 20%. That's what I was doing here, right? This is a whole 25%. 20 is fairly close. Knock a chunk off. Other people, little things, 13 is not half of 25, but it's fairly close. This would be half of 25, so a little bigger than that. That might represent 13%. So if we do a decent job with this, by the time we finish, my last piece of pie should kind of naturally already match, should naturally fit. So for favorite color of children, we still want a label, so I've already got that label right here. I'm just going to take advantage. My very, very poorly drawn circle. And for me, I always like to start here. There's a lot of other math reasons. You could technically start your first piece of pie anywhere, but I always like to start here. I'll start with blue. Again, 43.8%. If I went directly across, that would be 50. So let me angle that up a little bit. And this represents blue. And hopefully anybody looking at that, we see it's close. It's not a perfect piece of pie. I should quickly point out, this doesn't come up too often, but when we do these pieces of pie, I mean, this is a really big piece, but your normal pieces. When you cut a pie, a pizza pie, an apple pie, something like that, you don't cut this. You go from the center. You go through the center, you go through. That's what we're thinking. So even if we don't have perfect pieces like here through here, this one, and then this is a piece, but all those pieces of pie kind of have that connection in the middle. There's none of these random cuts. You go to a pizza parlor, you never see them cutting their pizza like this. It's like this. So there's my blue. And some people, just like here, they included the actual frequency as a part of the bar graph. Here, they include the percentage. And we keep going. The next one was green, and that was 20%. So now I'm going to start from here. A quarter, right? If I make that right angle right here, that would be 25%, but I need less than that. So that's a decent piece of pie that represents green. And there's my 20%. And now some people might even look and say, oh, these three, they're not really close enough. You know, these two are pretty close, and then people just want to like try and cut this up evenly, but it's still not quite that perfect. So I'm still looking at these three, and I need to cut this into one slightly bigger, one medium, and one small. So just looking at what room is left, I'm going to say, okay, let's do, here's my slightly bigger. This one is slightly smaller than this one, and this one is smaller still. Now, that's not perfect. Like I keep saying it. It's not that it has to be perfect, but if you ended up with a pie chart that looked like this, oh, let me finish, so I'm sorry. So this was the next big one, so that was red, 16.2%. Then we had, what was it, purple, and that was 13.1%. And then last, you know, you're getting too small. Instead of trying to write orange in here, you can pull it off, right? Just point, orange goes here, and that is 6.9%. And that's decent. You know, maybe you argue like, wow, 6.9, that still looks a little too close to that one. And that's where we could finagle a little bit, but it gives us decent sense. If your piece of pie at the end looks like this, blue, green, red, it's like, no, all those almost look exactly the same. It's not just that, oh, and actually, I'm sorry, I gave you, oh no, there's 5. Yeah, that's right. There are 5 pieces here. So it's not just to put a piece of pie for each color. Again, it's supposed to have that representation. So right now, if I did this and you're like, oh, blue, green, red, it's like, really? Blue and green look almost identical, but blue has more than twice the percentage that green has. So the piece of pie should be more than twice the size. So that would definitely not be correct. Okay, doing good, and we're just about done. The last couple of ideas here. And again, we'll get more practice. We've got a couple of examples that between the book and what we've done together, make sure you're going through the homework, but certainly on Monday, we'll do a couple more. Make sure if there's questions that we get good answers. So now, and again, a couple more. Gave you this as part of the packet, so you could see a few more bar graphs. You know, and they're doing per person CO2 emissions, total CO2, completely different size scales, but still bars for each individual country here. Again, common things, just like when I made my frequency table, we commonly go from biggest to smallest, so therefore the bars go from biggest to smallest. But that's not always the case though, right? I mean, just go back to the letter grade example. We didn't go biggest to smallest, we put our letter grades in order. So it still comes back to the idea. Sometimes, hey, it made sense to put the letter grades in order and then just let the frequencies be the frequencies. But an example like this, it might make more sense. Oops, sorry about that. In an example like this one, it makes a lot of sense to just put the countries from most to least. So now we see the order of the countries is changing from one chart to the other, but we still see that most to least. Okay. Here they do another quick simple pie chart where it's a perfect 25%, a perfect right angle here, a perfect right angle, and the 50%, that entire half a circle. Like I said, I think that's helpful because you do get a lot of percentage, a little bigger, a little smaller than 25%, a little bigger, a little smaller than 50. If you know a 25%, you could always cut that in half to get a sense for 12.5%. So little things to visually be able to see and help ourselves. But the last thing for today, for quantitative data, this is where we prefer histograms and line charts. So very quickly, a histogram is really a bar graph, but two things. Number one, that again, it goes with always quantitative data. So instead of having the categories across the bottom, the categories are going to be numeric. So that we'll have those numeric categories in order. So numeric categories are in order. And therefore, by doing it like that, now my bars touch. So just going back to the number grades one more time. We'll do this one more time. Going back to those number grades that we had, we bin them together. So we didn't list every single number across the bottom. We still used the endpoints of our bins, 70 to 74, 75 to 79. So notice that they used every 5 across the bottom here. And now that's 70 to 74, that is represented by this bar, the bar that starts at 70. Technically, this should be somehow indicate this is just shy of 75. But then the next bar starts at 75 and goes to 79. So instead of having 70 to 74, space 75 to 79, it makes sense to connect them because there's no separation in the data values themselves. There's no connection between different colors, but here, the nature of the numeric values, one category leads right into the next. So that's the only difference with a bar graph. With a histogram. We're still making a bar graph. We still have our title, we've got our frequency, and then we've got our scores. So it works just in that exact same way. Now, I can't make a histogram off of the favorite color because that doesn't make any sense. Like we said, the first part of a histogram, while it is a bar graph, it only goes with quantitative data. Similarly, this idea of a line chart. Once again, the x-axis is numerical. We once again have that same quantitative data situation, and we still have that frequency on the left side and our whatever this numeric value represents labeled and the numbers on the bottom. But now what we do, instead of having a bar, so this bar goes to 4 and that bar represents the students who scored between a 70 and a 75. In this one, notice here they've got this highlighted point. The point, they're aiming for the middle. So that is supposed to represent the people who got between a 70 and a 75 are that point. And there's 4 people. The people who got between a 75 and an 80 are represented by that point, and there's 7 people. To be quite honest, in this situation, it makes a lot more sense to use this over this. This idea that we could see the whole group. Instead of looking here now going backward and seeing, okay, that's the middle between 70 and 75, so it's the people who scored between those totals, it's so much easier to see that with a bar graph. But here, if my data involves time, the idea of a time series chart, that is where a line graph is perfect. So here they're giving us a time series chart that's telling us about homicide rate. It's not a particularly nice topic, but just to look through. Each point corresponds with a particular year, and then we can go over to see that now this is a homicide rate. It's not 5 homicides, it's 5 homicides per 100,000 people in 1960. It's right here. That's again, oops, no, I guess that's lining up more with like 6. Oh, I'm sorry, this is a rate, so it doesn't have to be a whole number. So maybe it's about 5.7 homicides per 100,000 people in 1966. So this, if we were given data like that, it's very easy to plot those as points. Technically, this is considered bivariate data, that we're getting 2 pieces of information that go hand in hand. So that's slightly different. I'm a little surprised the book brings that up here. But going backwards, let's just look at one more of those histograms. And they actually did a time series chart here as well. They did it on the same chart. But they gave us an example. They already binned our data. So they already gave us the frequency table. They're looking at the ages of Academy Award winning actresses at the time of the award. So how old were they when they won the award? So when we were collecting data, we would be like, well, this actress won at age 27. This actress won at age 32. This actress age 133. This one won at age 41. The data we would be collecting would be their actual ages. So we're getting numeric data. Well, how do we put that in a frequency table? We'd bin it. So now everybody who's between 20 and 29 goes in one category. Everybody between 30 and 39. Earlier with letter grades, they were binning in 5s. So we had our grades from 95 to 99, from 90 to 94. Here they're binning by 10. Is one better or worse than the other? You could have binned this by 5s. You could have went 20 to 24 and then 25 to 29. But this is what they chose. So now that we already have this information as a frequency table, well, now we go down here. My ages, I mean, you know, it's good habits, right? Starting at 0, but then going along, technically you could make a little jump and go 20 to 30, 30 to 40, 50. You know, again, we're going 20 to 29, but then the next category starts at 30. So it makes a lot of sense to get all the 10s on here. So ages 10, 20, 30, 40, 50, 60, and so on. And then we'd make our bars. Well, after we accumulated all that data, 30 actresses were between the ages of 20 and 29. So from 20 to 30, we made a bar. Notice, look at the totals here. How many people? 30, 34, 13, and then we're getting a lot of single digits. Once again, the scale. They didn't go up every 1 unit. And again, here they could have went 5, 10, 15, 20, but they chose to go by 10s. There's nothing wrong with choices here. This, just don't be silly. Don't go up to 100 actresses when no category goes further than 30. If you did that, your chart would be going up to here, but no bar goes higher than here. Make the chart effective. We want to see the top of the chart. We want to be able to see the bottom of the chart. So don't go crazy with that. So they chose by 10s. So 10, 20, 30, 40. And then we've got 10s here. So from 20 to 30, we've got 30 actresses. Our bar lines up perfectly with 30. From 30 to 39, we've got 34. Well, notice, it lines up about there. Little bit less than half. So we would assume, maybe we're not sure it's 34, maybe we think it's 33, but we've got a good sense. We can definitely see more actresses won between these ages than one between these ages, because the bar is taller. If you wanted to be more precise, this is fine, but this is where they could have included the exact values for each one. But like we said before, you don't have to. It's okay to leave it and have your audience have to ballpark about where that is. That is about 33, 34. Maybe you're slightly off and you think it's up here and you think it's 35. You're in the right ballpark. We're getting the right information. But just secondly, just to point out, they also snuck a line chart in here too. Your line chart has to start on the x-axis. So notice that's where it's like, where do I start here? Technically, this is my first data value. I went halfway between 20 and 29, and I put a point to represent the 30. Then I went in between 30 and 39, put a point to represent the number of actresses. In between 40 and 49, put a point to represent the number of actresses. And then at the end, we just connected the dots, essentially. So that's it, everybody. That's really all there is to it. I mean, again, if you want to flip through a little more, we pretty much covered everything we've got. Next, you're getting into the homework. So just to get some extra practice. Terminology. Well, qualitative and quantitative are musts. Not that you have to have a verbatim definition, but just the nature of the question. Is the data qualitative, quantitative? You have to be able to understand the difference in your own head to get that. But the others, what is a histogram? What is a line chart? What is a pie chart? What is a bar graph? I would never ask a verbatim definition, but if I say make a histogram, if I ask you, would a histogram be more appropriate than a bar graph? We should be able to answer little questions like that. So that's it. Make sure you get into the homework for 5C. We'll do a little bit more from 5C, get a little extra practice, clarify a few points, especially if there are any questions, and then we'll get into 5D a little bit on Monday. That's it, everyone. Have a good week. I'll see you on Monday.